Hey, how's it going and welcome back. If you followed along in the last video, I went ahead and walked through the UNet convolutional neural network, and I kind of talked about the main ideas, basically kind of explaining and went through the architecture and kind of the different building blocks and kind of the what the model's used for and how it's used for semantic segmentation, the per pixel classification of input imagery. So today I wanted to go ahead and walk through how to go ahead and code up a UNet model in Tensorflow, and then also kind of talk about a few of the nuances and how you can interchange a few different features within the UNet and kind of plug and play a few different ideas to kind of expand upon what the original paper talked about. So let's go ahead and get started. So go ahead and open up your code editor and create a Python file. Go ahead and just name mine models. So like I had said before, this is going to be in TensorFlow. So I'm going to go ahead and import TensorFlow. And then I'm going to go ahead and import some layers. Okay, so to kind of highlight the architecture, I'm going to go ahead and pull up. A diagram of it so we can go ahead and keep that on the screen, or at least have access to it while we're working through this. That's not it. Go ahead and maybe I'll just go ahead and do this. Here we go. Okay, so yeah, if we kind of remember, basically it's built up of two convolutional blocks, then we have a max pooling operation, two more convolutional blocks, max pooling, and then that kind of happens all the way down the encoder, and then the decoder is kind of the opposite, right? So you're kind of decoding it back out, and then you just have these skip connections going between the encoder and the decoder. So all right, so let's go ahead and first thing we're going to start with is we're going to code up one of those convolutional blocks. So we're going to go ahead and make a function that's conv block, and it's going to have two convolutional layers. So we're also going to give it a parameter of number of filters. So in the original paper, it started out with 64 filters. Batch norm equals false. So this is kind of an addition onto the original paper, where we're actually going to add some batch normalization to these layers, and they're also going to add in dropout. So batch norm and dropout are both kind of regularization techniques. They kind of help add in. They add in regularization that helps prevent the model from overfitting, right? So they're common practices used in convolutional neural networks, and have just kind of adding in the functionality is going to kind of expand upon the original paper and is in an improvement. So, okay, so the first convolutional layer is going to be a convolutional 2D. We want to pass the number of filters. We want to have a 3x3 kernel, because if you remember on the original paper, go ahead and take a look again. If you see here, we have conv 3x3, and then we have ReLU activation. So go ahead and do 3 by 3. So, and then we're going to go ahead and do padding equals same. So this means that when it performs a convolutional operation, if you have valid padding, the actual convolutional operation will actually pool the size spatially of the input feature, right? So if you set padding equal to same, then basically what it does is it pads around the input image or the input feature, and it makes it so that the convolutional operation doesn't actually spatially pool the feature. It keeps it the same size as the input size. And then we are going to do, yeah, right, okay. Then we're going to pass that over the inputs. So here I would like to just kind of comment and say that here we're using normal convolutional layers, right? Based upon the paper. If you wanted to interchange that, however, though, there's this other thing called separable convolutional layers. And they are slightly different than the normal convolutional layers. Normal convolutional layers, they process all of the channels of the input feature space together, and the separable convolutional layers don't. They actually process each channel independently from each other, and then they kind of concatenate or merge the features together at the end, right? So it's the idea behind it is actually supposed to be computationally more efficient, and then it's also processing each channel of the feature space independently, right? So if and making the assumption that they aren't necessarily like correlated to each other, so it can create more robust features. I personally use separable convolutional layers quite a bit, so here would be the time to interchange that, and in your code if you would like to. You don't have to. You can go ahead and just keep it the same as the paper. And then if batch norm, since it's a parameter and it's an option, so if you want to use batch normalization, then we're going to go ahead and apply that on the last axis of the input feature space, so the channels of the input tensor. And then we're going to apply that to the first conv block. And then we're going to apply our activation function. So there's some debate on whether or not applying the activation function before the batch normalization or after the batch normalization is better. My understanding is that it's actually better to apply it afterwards. And in the original paper, they use regular rectified linear unit, and here we're using what's called leaky rectified linear unit. And the only difference is the original ReLU or normal ReLU, basically any values that are less than 0 get cropped to 0, and then anything greater than 0 maintains keeps its value. Leaky ReLU actually allows a few slightly below 0 values to be allowed in, and it doesn't crop them to 0. The idea behind it is it kind of helps with some of the vanishing gradient problems. Because if you're kind of or you're cutting everything off or clipping everything to 0, sometimes you can, especially in these really deep networks, you can run into kind of some of the vanishing gradient problems. So I like to use leaky ReLU. There's actually a lot of different variants of ReLU, like I think it's GeLU. There's tons of them, right? So you can go ahead and look them up. Go ahead and pick which one works for you, or experiment with them. They all behave similarly, but kind of enough different that it doesn't hurt to try them out, see if you get better results. So okay, so now we're going to go ahead and create the second convolutional layer. So it's kind of very similar to the first one. Going to have the same number of filters, padding equals to same, and then we are going to call that on the first convolutional layer. And then just like before, we're going to go ahead and do the whole batch norm thing. So if we want to apply batch norm, we're going to do that. And then after the two convolutional operations, this is where we're going to go ahead and add in the dropout. So if our dropout probability is greater than 0, then we're going to want to go ahead and apply that. So dropout drop out probability, and then apply that to our second convolutional layer. And then we're going to go ahead and return that second convolutional layer. So if you don't know what dropout is, basically these convolutional layers, or even fully connected layers. So when you're working with normal multi-layered perceptrons or densely connected neural networks, what dropout does is it basically forces it randomly drops out some of the parameters of the model or of the layer, right? So basically the idea is let's say I say dropout probability of 30%. So each time it runs, it'll randomly drop out 30% of the neurons, so that, and basically what it does is it forces the model to not become too dependent on specific biased feature spaces, right? It makes sure it doesn't learn like biased features, because it needs to learn robust enough features that if it were to lose 30% or whatever percent dropout of the neurons randomly, it has robust enough features to still perform well and to properly classify the things you're trying to classify. So that's kind of the basic idea, right? So, okay, so here we have the convolutional operation. So go ahead and take a look. So the two convolutional blocks here, for the output, their output is going to be this particular thing here. And then the next thing we need to do is pass it through the max pooling function, right? So let's go ahead, and we're actually going to make what's called the encoder block. So I'll explain that in a minute here. Oops. Okay, so like I had said, we're going to need to make sure our skip connection is our convolutional block then has a skip connection. So we take as an input that skip connection, and we're going to pass it through a convolutional block. Here to this conv block, I'm passing whatever the parameters were defined by the encoder block, so I'm just passing them along. Okay, so let me just kind of code one more thing up, and then here I'm going to kind of walk through this and explain this. Okay, so here you see I kind of coded up two different things, right? So next layer using a normal convolutional block, and then next layer using the max pooling. So like I had said, the next operation is some sort of pooling operation. In the original paper, they used what's called the max pooling layer. And basically what that does is it looks at 2x2 blocks, and it takes the maximum value, and then it perpetuates that value on. So it looks at the maximum activation, or the maximum activated feature in that little block, and then that's perpetuated on in order to pool and condense the features spatially. That generally works really well. But there are other ways of pooling, right? And especially when you're trying to do some sort of local operation like semantic segmentation, right? Where you're trying to get that per pixel accuracy. Sometimes just perpetuating the maximum activated feature isn't necessarily the best. Sometimes you want to do like a normal convolutional layer or a normal convolutional operation, but instead of having stride of 1, you set your stride to 2. And then what that does is it'll also do the to the power or times 2 pooling, right? So it'll pool it down by 2. But it does so in a way that you're not necessarily pulling the maximum feature from the area, right? Actually, it's able to learn what type of pooling operation it's going to do. So it can kind of learn, instead of, oh, I want to always take the maximum. Maybe it kind of takes different maybe stats, or different, it looks at different features that are then perpetuated on. So you can use either one of these. I guess in spirit of the paper, we'll just go ahead and leave it with the max pooling, but you maybe kind of understand the concept at least. So we're gonna go ahead and return the next layer and the skip connection. Okay, so let's go ahead and take a look at that paper again. All right, so we kind of have the basic modules we need in order to build up the encoder. So the encoder portion of the network. So let's go ahead and do that. Okay, we're going to go ahead and define the UNet model. Have an input size. Standard is, 128 by 128, or like 256 by 256, or like 512 by 512. Basically, you need to make sure that it's your input spatial size is at least to the power of 2, some power of 2, right? So because it's symmetrical, so they need to be able to, during the expansive part of the decoder portion of the UNet, if it's not to the power of 2 and it tries to pool things by 2, you're not going to have things lining up properly. So just something to keep in mind when you pick that input feature space. So base number of filters is 64. Number of classes can be anything. We'll just put 5. Batch norm. I like to use batch normalization. And then dropout can be a NumPy array of zeros. And there's going to be 9 convolutional blocks. So we're going to go ahead and do zeros of 9. So go ahead and import NumPy. Okay, so our inputs is the input layer with our input size. This is just building up our model. So since we're using the functional API, we'll be able to call the summary. And since we provided an input size, it will be able to actually print out the summary of our model when we're all done. Okay, and then we're going to go ahead and encode or code up the encoder. So encoder block 1 equals encoder block. Okay, so yep, we're passing the batch normalization. We want to use the first dropouts in the list, or an array of dropouts we've passed to it. Go ahead and since there's 4 of them, if we take a look, kind of look at the here again. So we have 1, 2, 3, or we have 1, 2, 3, 4, right? So we have 4 encoder operations. All right, so and if you remember correctly, go ahead and change these. Okay, so if you remember correctly, what we take as input into the encoder block, or actually what's output, is you have your next layer, and then you also have your skip connection. So indexing 0, so the first one is the next layer. We want to send that to the next encoder block. So encoder block index 0 goes to the next encoder block, and then that skip connection is what's going to be used in the decoder portion of the model. So go ahead and continue that on. 3 And then each time, or each level of the UNet, we increase the number of filters by a power of 2. And then here we go, continue passing the proper dropouts. And there you go. So there is the encoder portion of the UNet. And then the next part is the bridge. So it's kind of the bottom portion before we send things back to the decoder. And there we have it. So the next portion is the decoder. And in order to do that, we need to actually code up the decoder block. So we're going to go ahead and do that quickly. Okay, so much like the encoder block, we have except for here we have 2 inputs because we're gonna have the expansive input, so the input that's coming from the encoder, and then also the skip connection input. And then just like the encoder block, we have number of filters, batch normalization, and then our dropout probabilities. Okay, so the first thing we're gonna do is we need to upsample the input that's coming from lower down in the network, right? So it's at a different spatial feature size, so we need to upsample it so that it's to the same feature size as the skip connection. So here we see, this is a good example of it. Down at the bottom, we have an input feature size that's spatially 30, and then here we have it's higher. So I think actually these numbers are a little misleading, but so for example, if we take a look at this, if we start with 256, with our UNet, I'm pretty sure the bottom one of the bridge will be 16 by 16, and then obviously the one above that is going to be at 32 by 32, right? So we need to upsample the 16 by 16 up to the 32 by 32. Okay, so in order to do the upsampling, we're going to go ahead and use what's called a conv 2D transpose layer. So we're going to pass this the number of filters. We're going to do 3 for the kernel size, and then strides is going to equal 2 because we're trying to upsample by a power of 2, and then padding is equal to same. And we're going to apply this to the expansive input because we need to upsample that to the size of the skip connection. And then we are going to merge those together, or we're going to add them, concatenate them together, right? So go ahead and call that. And we're going to do this on the last axis. Oops. And then we're going to pass that through another convolutional block. And then we are going to return the convolutional block. So kind of take a look. So if you see, we have this expansive input here, we have the skip connection here, we concatenate them together, and then we pass them through another convolutional block, and then we're going to continue to do the same, right? So we're going to upsample again, and so forth. So now that we have our decoder block, we can go ahead and build up the decoder of the UNet. So the first expansive input is actually the bridge. And the first skip connection comes from the encoder block 4. And then here we're going to do the reverse, right? So we're going to, since we're starting at the bottoms for the number of filters and the features, we're going to start at 8 and work our way back up to the number of filter times 8 back up to just the number of filters. And then of course, go ahead and pass batch norm again, and then dropouts. To 5. And then since this is symmetric, there's 4 decoder blocks. And then here we're using the previous decoder block as the next expansive input to each successive block. So we have decoder block 3 and then 2. And then here again, coming from the encoder blocks is our skip connections. So we're actually going to do 3, 2, and then 1. And then again, the number of filters is going back up to 64, so times 2, and then indexing the correct dropouts. And there we have it. So there is the encoder and the decoder, right? So the next thing we need to do, now we've encoded the input feature. So here's the inputs, we've encoded it, now we've decoded it. Now the next thing we need to do is we need to do our convolutional 1-by-1 operation. The convolutional 1-by-1 operation is going to give us our output feature map and our output probabilities. So let's go ahead and do that. So like I'd kind of mentioned before, this is kind of dependent on the number of output classes, right? So that was one of our parameters, is number of classes. So if it's 2 classes, we have what's called a binary classification problem. So what we're going to have to do there is then, so here's the 1-by-1 operation here for the convolutional layer. So we have kernel size of 1 and then stride of 1, padding equals same. And then we're going to pass the last decoder block to this. And then our output is going to equal activation and then sigmoid. Because what that will do is then for each pixel, it'll then take the value of that pixel and map it to a number between 0 and 1, right? So if it's greater than 0.5, generally that's what we consider, the probability is high enough to be classified as class 1. And then if it's less than 0.4, or greater than or equal to 0.5, then it'll go to 1 as you round it up. So it's classified as class 1. And then if it's less than 5, then it's class 0, right? So binary, 0 or 1. That's kind of how we deal with that. And then else, so if the number of classes is greater than 2, right? We're going to go ahead and do what's called a multi-class, right? So this then becomes, instead of the output map being the number of pixels by 1 channel, right? Which was for the binary, we have just 1 channel output. We actually want the number of classes as the number of channels for our output. Kernel size 1, padding equals same. And then we're going to go ahead and pass our decoder block 1 to that. And then output is going to also be activation, but this time it will be softmax. And then pass our convolutional 10 block to that. And then we're going to create our final model object. So keras, tf.keras.model. I'm going to fix this typo here. And then in order to do that, we pass inputs equals inputs. So this is our inputs layer. And then we're going to go ahead and do outputs equals our output. As our, either whatever one will happen, or it'll be our output layer. And then we're going to go ahead and name it equals UNet, right? So and then for our final function, what we're going to do is we're going to go ahead and return model. So then that will return our UNet model. So now that we've done finished coding it up, we can I can show you what that would look like. So we're gonna go ahead and write a little script here. So if name equals main, what we're gonna do is we're gonna go model equals UNet model, and I'm going to call that function just with the base already coded in parameters. And then what we're going to do is we're going to go ahead and print out model.summary. And we'll go ahead and take a look and see what that looks like. Okay, so I'm going to go ahead and move over to that directory. I'm going to go ahead and activate my Conda environment. And then I'm going to go ahead and call this script. Give it a minute here to load. TensorFlow takes a little bit to load sometimes. Cannot import separable convolution. Give me 1 second and I'll be right back with you. Okay, so I actually spelled separable wrong. I had a E here instead of an A, so went ahead and fixed that, and we should be able to go ahead and run the script now. Go ahead and call Python models.py. And what this will do is it should print out a summary of our UNet model. And there we have it. So total training parameters down here at the bottom is 34.5 million. And let's go ahead and walk through the summary real quickly, just kind of wrap it up. So we've got, our first input layer, which is 256 by 256 by 3. And then you can see that this is working properly. We've sent it through the first convolutional block, and it's created 64 features because that's the number of filters we wanted. And then as we go deeper into the network, it's spatially pooling. So we're getting smaller, 128 by 128, but then it's actually growing in features as we've gone up to 128. So then as we continue, we get down to 64 by 64 by 256, 256 features, but it's only 64 by 64 pixels in size spatially, 32 by 32 by 512. And then we get down here and we get down here to the bridge. So then we have 16 by 16 by 1024. And then as we follow up the decoder, it kind of goes back the way it came, 32 by 32 by 512. And then here you can see the concatenation occurring, right? So you can see the layer, it concatenates the features together. That's why we had to upsample the expansive input, was to make sure that it has the same spatial feature size, so then we could concatenate them together to get 1024 filters. And then we sent it through our convolutional layer, and then so it convolves it back to 512 features. And then we continue up 64 by 64 by 256, 128 by 128. And then finally, as our output, we get back up to 256 by 256 by 64. And then for our final output, here you can see our output array is 256 by 256 by the number of classes. And since we passed 5, it's by 5. So there you have it. There's kind of a simple UNet, and then also kind of some ideas on how you can expand beyond the original paper, adding in maybe separable convolutional layers, using different types of activation functions, or even adding in batch normalization and dropout. So I hope you enjoyed. Next videos, or the next couple of videos, I kind of plan on working through a couple different semantic segmentation architectures, and then also working through some data sets and working through how to get these things running and training on data and using them to get some segmented results, right? So I hope you enjoyed. I hope you see you next time, and